Far beyond the reaches of our solar system, in the vast emptiness of the cosmos, exist some of the most enigmatic and extraordinary phenomena ever discovered: neutron stars. These stellar remnants are the last vestiges of massive stars that have ended their lives in a spectacular explosion known as a supernova. Yet, even after their death, they continue to puzzle and captivate astronomers, offering us a glimpse into the most extreme conditions of the universe. Among their many mysteries, one stands out above the rest: their magnetic fields. These magnetic fields are so powerful, so incomprehensibly strong, that they defy all expectations and challenge our understanding of physics. What are they? How do they form? And why are they so incredibly intense? The answers may hold the key to unlocking some of the most profound secrets of the universe. To understand neutron stars, we must first understand their origins. A neutron star forms when a massive star, many times the size of our Sun, exhausts the nuclear fuel that powers its core. With no more fuel to hold back the crushing force of gravity, the star collapses in on itself, triggering a supernova explosion. The outer layers of the star are violently ejected, while the core remains, compacting into an incredibly dense object. This new object, a neutron star, is truly extraordinary. It is so dense that a single cubic centimeter could weigh about 400 million tons, far beyond anything we experience here on Earth. To put it in perspective, a teaspoon of neutron star material would be heavier than all of humanity combined. The collapse is so extreme that the matter inside the star is crushed to the point where electrons and protons are forced together to form neutrons, creating a star made almost entirely of neutrons. But it's not just the density that makes neutron stars unique. These stars can spin at incredible speeds, up to 700 times per second in some cases. A neutron star's rapid rotation and immense gravitational pull generate forces that shape everything about its behavior. And yet, the most mysterious and fascinating characteristic of these stars is the magnetic field that surrounds them. Magnetic fields are a fundamental force of nature. We experience them daily in the form of magnets or the Earth's magnetic field, which protects us from harmful cosmic radiation. But the magnetic fields around neutron stars are unlike anything we can imagine. They are not just strong, they are mind-bogglingly powerful. A neutron star's magnetic field can be 1,000 trillion times stronger than the strongest magnet ever made by humans. This immense magnetic power has a profound influence on the star itself, as well as on everything around it. Imagine, for a moment, standing next to a neutron star. If you were close enough, the magnetic field would be so intense that it could rip apart atoms and even distort light. The magnetic forces inside the star can warp space and time themselves, bending the very fabric of the universe. And the question remains, how does such a powerful magnetic field come to exist in such a small, dense object? The formation of these magnetic fields is one of the greatest mysteries in astrophysics. Some scientists believe that these magnetic fields are born in the heart of the star during its collapse. As the massive star's core implodes under gravity, the rapid rotation and extreme density may stretch and twist the star's magnetic lines, amplifying them to unbelievable strengths. This is similar to how the Earth's magnetic field is generated by the movement of molten iron in its core. Only here, the magnetic field is created by the extreme conditions of neutron star matter. There's another possibility. The neutron star itself is composed of a strange and exotic mix of particles, neutrons, protons, and electrons, all interacting under immense pressures. These particles move and interact in ways that could generate a magnetic field far beyond anything we can replicate on Earth. It's as if the very matter inside the neutron star is constantly in motion, generating powerful electromagnetic forces that twist and amplify the magnetic field. But no matter which theory is correct, one thing is clear. The magnetic fields around neutron stars are created under the most extreme conditions imaginable. They exist in a delicate balance, influenced by the star's rotation, its internal composition, and the physics of extreme density. While most neutron stars have incredibly powerful magnetic fields, there are some that stand apart, magnetars. These extreme stars possess magnetic fields that are far stronger than those of typical neutron stars. A magnetar's magnetic field can be up to 1,000 times more powerful than that of a regular neutron star. To give you a sense of scale, the magnetic field of a magnetar is so intense that it could wipe out every single piece of data on a credit card from thousands of miles away, simply by being nearby. The sheer force of a magnetar's magnetic field causes the star to crack open, emitting violent bursts of X-rays and gamma rays, some of the most energetic radiation in the universe. These bursts are so powerful that they can be detected by space telescopes light years away. In fact, magnetars are considered to be one of the leading candidates behind mysterious cosmic phenomena known as gamma ray bursts, massive explosions that release as much energy in a few seconds as the sun will emit in its entire lifetime. Yet, despite the awe-inspiring nature of magnetars, their magnetic fields are not fully understood. What causes them to be so powerful? Why do they generate such intense bursts of radiation? And how do these magnetic fields evolve over time? These questions remain central to the ongoing investigation into these cosmic oddities. Neutron stars don't just affect their immediate surroundings. They have a profound impact on the entire cosmic environment around them. In binary star systems, where a neutron star orbits a companion star, its magnetic field can pull gas and material away from the companion. This material forms a hot, glowing accretion disk as it spirals toward the neutron star. As this gas is pulled in, it accelerates to incredible speeds and heats up to millions of degrees, releasing intense radiation, particularly in the form of X-rays and gamma rays. The neutron star's magnetic field can also produce powerful jets of particles, shooting them out from its poles. These jets can travel across vast distances, forming what are known as pulsars. Pulsars emit beams of radiation from their magnetic poles, and as the neutron star spins, these beams sweep across the sky, creating the characteristic pulses of light that astronomers detect. These regular flashes of light are like cosmic lighthouses, guiding our understanding of the fundamental physics at play inside neutron stars. Despite decades of research, the magnetic fields of neutron stars remain one of the greatest unsolved mysteries in astrophysics. Why do some neutron stars possess such incredibly strong magnetic fields, while others are comparatively weaker? How do these fields evolve over time? What role do these magnetic fields play in the life cycle of neutron stars? And perhaps most tantalizing of all, how might these extreme magnetic fields help us understand the most fundamental forces of nature, from gravity to quantum mechanics? The answers to these questions lie at the frontier of modern science. With the help of the world's most powerful telescopes, advanced simulations, and future space missions, scientists are working tirelessly to uncover the secrets of neutron star magnetism. Each discovery brings us closer to unlocking the cosmic mysteries of these extraordinary stars, helping us understand not just their nature, but the very structure of the universe itself. Neutron stars are more than just remnants of dying stars. They are the cosmic laboratories where the most extreme forces in the universe converge: gravity, magnetism, and quantum mechanics, all interacting in ways that challenge our understanding of physics.